We've developed a lot of concepts related to deformations and equilibrium, culminating in the Tonti diagram. We've learned different things about the stiffness matrix. What we want to do now is put it all together and write code that can do structural analysis. One last thing we need to do before we can do that is to talk about how to assemble the stiffness matrix. And that's what we're going to do in this video. So one common situation that we deal with is, given the loads on a structure, calculate the displacement. So in other words, given the joint load vector P, calculate U. Or in other words, solve the equation K times U equals P. Now K equals B transpose EB is a stiffness matrix, but it's not a good idea to do this literally. Think about why. It has to do with the sparsity of K. We'll end up multiplying by lots of zeros. So instead, what we want to do is what we call assemble the K matrix. To do this, first we number the degrees of freedom. So let's take again the example truss that we've been using as a running example, with the nodes numbered 1, 2, 3, 4, members numbered 1, 2, 3, 4, 5, 6. And then instead of calling the displacement, labeling the displacements, we'll number them 1 to 5 as shown here. Notice that we're not numbering the fixed degrees of freedom. So because there are 5 degrees of freedom, the stiffness matrix will end up being 5 by 5. Now if we look at the B matrix, each row of the B matrix corresponds to a particular member as shown here. And the B transpose matrix is therefore each column of the B transpose matrix corresponds to a member. We can use this fact to write the stiffness matrix as the sum B of each member times E of each member times B of each member, okay, summed over all the members. So what I'd like you to do is to just demonstrate that this can in fact be done. So let's take the example of member 5. So the stiffness matrix of member 5 is its B transpose times its E times its B. Now that'll end up being 4 by 4. Now if we look at that member, it connects to degrees of freedom 2, 3, and 1. And the vertical degree of freedom at joint 2 doesn't exist. So because it's connected to degrees of freedom 1, 2, and 3, its stiffness matrix will take the positions 1, 2, 3, 1, the block 1, 2, 3, 1, 2, 3 in the structure stiffness matrix. So for each member, we'll compute the member stiffness matrix and then put that block into the structure stiffness matrix like this. And this process is called assembly. So in the next video, we will go through a code that actually puts it all together and does a structural analysis. And in that code, we'll use this example of a truss that has it's a 6 meter by 6 meter geometry, and it's got these area properties. And we'll use this example to demonstrate the code.